You're working on something really important. You feed an AI tool this massive document, maybe, a 100-page financial report or a huge legal contract, and you wait.
Right, you just sit there.
Yeah, cursor blinks. And when it finally gives you an answer, you ask a follow-up question, only to realize the AI has completely forgotten the context from page 1.
It's so frustrating.
It is incredibly frustrating. You have this hyper-advanced supercomputer at your fingertips, and suddenly it acts like it has the memory span of a goldfish. So, welcome to the Deep Dive Lab. Today, we're exploring the hidden bottleneck choking modern AI and the incredible lengths scientists are going to fix it.
And it is a fascinating journey.
It really is. We've got papers from IDNRX, research from massive tech giants, so we're going to break it all down. But to start, here's a strange question. Why does a machine capable of processing trillions of calculations a second suddenly hit a physical wall when trying to remember a long conversation?
Well, it really comes down to a fundamental mismatch in how computers are actually built. I mean, we expect these large language models to be flawless, omniscient entities, but they are bound by very real microscopic physical limitations.
So it's not a software glitch, it's hardware.
Exactly. To understand why your AI suddenly forgets page 1, you have to look at its brain, which is the GPU, or graphics processing unit. Now, modern GPUs are absolute computational monsters.
Just insanely fast.
Right. But they are starving. They are constantly starving for data because the memory systems feeding them simply cannot keep up with their processing speed.
Oh, I see. So it's not that the brain is slow, it's that you can't hand it the books to read fast enough.
Yeah.
The bottleneck is the delivery mechanism.
That is the defining problem of modern computing right now. For years, the gold standard solution for this delivery mechanism has been something called HBM, or high bandwidth memory.
High bandwidth memory, okay.
Yeah. And this is a specific type of volatile memory, meaning it forgets everything the second the power turns off, but while the power is on, it is astonishingly fast. It's physically co-packaged right next to the GPU on a tiny piece of silicon.
Okay, so to visualize that speed, HBM can move data at around 2 terabytes per second, right?
Give or take, yes.
Which is wild. Imagine downloading hundreds of high-definition movies in a single second. If HBM is moving that fast, I'd compare it to like a Formula One Ferrari.
That's a good way to look at it.
It's blazing fast on the track.
Yeah.
But the glaring issue with a Ferrari is that it has a tiny glove box. It physically cannot hold much cargo. A typical HBM stack maxes out around, what, 36 to maybe 64 gigabytes?
Yeah, somewhere in that range. Which sounds incredibly spacious if you were just buying a personal laptop at Best Buy.
Oh, for sure.
But for an enterprise AI model that's reading libraries of data, it is just a drop in the bucket. When the AI's active memory requirements exceed that tiny glove box, the system panics. It is forced to fetch the overflowed data from traditional NVMe SSDs.
Right, the standard hard drives.
Exactly. Those are the storage drives built using NAND flash memory.
And NAND flash is completely different fundamentally, right? It's non-volatile.
Right. It doesn't forget.
It traps electrons in little microscopic cells so it remembers your data even when the power is pulled. It's literally the same cheap, high-capacity stuff inside the thumb drive sitting on your desk.
It is. And because it's so cheap and dense, an SSD can hold terabytes upon terabytes of data.
Okay, but if HBM is the Ferrari, the SSD is like a massive, lumbering cargo ship.
Yep.
It holds an ocean of cargo, but it moves at an absolute crawl compared to the GPU. So you get this massive traffic jam.
A huge jam.
The multi-thousand-dollar GPU just sits there, completely idle, twiddling its thumbs, waiting for the cargo ship to arrive so it can read the next sentence.
And that right there is the memory wall.
But wait, let's think about the physical engineering here for a second. If the Ferrari is fast but small, why not just, buy 10 more Ferraris? Why don't we just glue a bunch more of these ultra-fast HBM chips right next to the GPU to get more glove box space?
Well, physics gets in the way of that seemingly obvious solution. Hardware engineers run into something called the shoreline constraint.
The shoreline constraint. Okay, paint a picture of that for us.
So imagine the GPU processor as an island. To get data on and off that island at 2 terabytes a second, you need bridges. Lots of them.
Makes sense.
In a computer, those bridges are microscopic electrical connections. The perimeter of your GPU island is your shoreline. You literally run out of physical perimeter space around a modern chip to attach more of these ultra-fast HBM stacks.
Oh, wow.
Yeah, there is zero real estate left to build another bridge.
So you are completely landlocked by the physical dimensions of the silicon chip itself. You can't make the perimeter bigger without making the whole chip massive,
Right.
which makes it prone to breaking.
Exactly. And the demand for memory isn't slowing down to accommodate that constraint, not even a little bit. Let's look at advanced large language models like Llama 4. These models now support what's called a 10 million token context window.
10 million tokens, meaning you could upload a dozen massive textbooks, financial transcripts, code bases all at once, and the AI is supposed to hold all of that in its active working memory.
Right. And to keep track of all those tokens during a conversation, the AI uses a key value cache, or KV cache.
Key cache, got it.
Think of the KV cache as the AI's scratch pad for the ongoing interaction. It stores the mathematical representations of everything you've talked about so far. For a 10 million token workload, that scratch pad expands to a staggering 5.4 terabytes of data.
Wait, 5.4 terabytes just for the scratch pad?
Just for the scratch pad.
That is insane. Which brings us back to the Ferrari problem.
Yeah.
If an HBM chip only holds 64 gigabytes, storing 5.4 terabytes of active memory in HBM means you'd have to string together dozens and dozens of incredibly expensive, power-hungry GPUs, not because you need their computational power, but purely to harvest the storage space from their attached memory.
Exactly. It becomes economically and environmentally disastrous. You'd be buying racks of million-dollar supercomputers just to use them as glorified flash drives.
That's hilarious, but also terrible.
Right. So researchers realized they were trapped. They couldn't just keep pushing the Ferrari. And they couldn't rely on the slow cargo ship. They needed a third vehicle, something with the speed of the Ferrari and the capacity of the cargo ship.
So how did scientists figure this out? This is where the story gets really interesting, because it brings us to this massive breakthrough. Enter high bandwidth flash, or HBF.
Yes, HBF.
This technology was developed by SanDisk and SK Hynix, with Samsung recently jumping into the race as well. And the wild part to me is that they didn't discover some exotic new element on the periodic table to do this.
No, not at all.
They took standard 3D NAND flash again, the exact same core technology in your cheap thumb drive, and they radically re-architected it.
Right, they looked at the structural flaws of how we build memory. Standard NAND flash relies on something called wire bonding. Basically, tiny wires run along the edges of the memory chips to connect them. But moving electrical signals across those wires introduces electrical resistance, which limits how much data can move at once. HBF completely discards that sprawling layout. Instead, engineers vertically stack up to 16 layers of this 3D NAND flash.
Let's expand on that visual because it is stunning when you really think about it. Wire bonding is like building a sprawling suburban neighborhood. If you want to deliver a message from one house to another, the delivery driver has to drive miles down winding roads. It takes time, and there's a lot of friction.
Right.
But HBF takes those houses and stacks them into a 16-story skyscraper.
And to deliver the message in that skyscraper, they don't use winding roads. They drill an elevator shaft straight down the middle.
That is so cool.
They use microscopic wires called through silicon vs or TSVs. They literally drill thousands of microscopic holes vertically through the silicon chips to connect the layers directly.
So the electrical signal just drops straight down the elevator shaft, instant communication.
It gets better. At the base of that memory skyscraper, they use a proprietary technique called CBA, or CMOS directly bonded to array.
Okay, CMOS directly bonded to array.
Right. CMOS is essentially the logic brain, the controller. They physically fuse the massive memory array directly onto that logic controller at the base. It acts like an ultra-efficient lobby directing the elevator traffic.
And the specs coming out of this skyscraper architecture are just mind-blowing. By eliminating the winding roads and using those vertical TSV highways, HBF delivers 1.6 terabytes per second of read bandwidth.
It's incredible.
That is within 2.2% of the speed of unlimited HBM. It is practically matching the Ferrari. But because it's built out of dense NAND flash, it packs up to 4 terabytes of capacity in a single stack.
Yeah.
It's giving you up to 16 times the capacity of HBM at a similar cost.
Yeah, the capacity is massive.
I mean, Kioxia actually just prototyped a 5 terabyte flash module, pushing 64 gigabytes per second of sustained read bandwidth.
It completely bypasses the traditional bottlenecks we've been stuck with for years.
Okay, hold on though. I have to play devil's advocate here for a second, because anyone who has built a PC or managed a server knows about SSD wear and tear. Flash memory has a finite lifespan, right?
It does, yeah.
Every time you write data to a cell, by trapping those electrons, the physical cell degrades slightly. If an AI is constantly thinking, updating its context, and churning through billions of parameters, wouldn't that constant rewriting fry an HBF chip in a matter of weeks?
Well, that is the exact reason why HBF isn't meant to be a universal replacement for all memory. You've hit on the fundamental twist of how researchers are deploying this. HBF is designed specifically for AI inference, not AI training.
Ah, let's pause and unpack the difference between training and inference, because that distinction is everything here.
It really is. So training an AI is the initial messy phase. You are feeding the neural network the entire internet, and it is constantly adjusting billions of parameters to learn the underlying patterns of human language.
Just constant trial and error.
Exactly. That requires a massive constant churn of writing, erasing, and rewriting data. You would absolutely destroy an HBF chip doing that.
Right.
But inference is when you are running the finished trained AI model. When you ask ChatGPT a question, that's inference. The model's weights, its fundamental knowledge of how to speak English or code in Python, those are static.
Oh, so once it knows the rules of gravity or the syntax of a coding language, it never needs to rewrite those rules. It just references them.
Precisely. Under this new architecture, the HBF is used exclusively to store those static weights in the pre-computed KV caches. It acts as a massive, high-speed, read-only library. By treating it this way, engineers entirely sidestep the 100,000 write-cycle endurance limit of NAND flash. You are just reading from it.
And reading doesn't damage it.
Right. Reading causes virtually no wear and tear.
That is brilliant engineering. You isolate the weakness of the material by exclusively leaning into its strength. And we're already seeing how this changes the physical layout of supercomputers. I mean, there's a fascinating study published in the journal IE Computer Architecture Letters by Minyo Ha from SK Hynix Research. He proposed something called the H-cubed hybrid architecture.
Yeah, the H-cubed architecture is just a masterclass in system co-design. Minyu Ha and his team didn't just throw HBF into a standard server rack and hope for the best. They designed a system that daisy-chains the Ferrari and the skyscraper together on the same silicon interposer right next to an NVIDIA B200 GPU.
And an interposer being the high-tech digital foundation that allows two distinct chips to talk to each other as if they were a single piece of silicon, right?
Yes, exactly.
Yeah.
They built a custom-based die on that foundation that splits the traffic intelligently.
How so?
Well, if the GPU needs to do high-speed dynamic scratch pad work, the fast writing and erasing you mentioned earlier, it routes that data to the local HBM. But if it needs to read the static weights or pull up massive historical context, it passes that request right through the HBM and accesses the massive HBF skyscraper.
So the GPU doesn't even have to think about where the data lives. It just asks the foundation for the information, and the hardware automatically routes it to the most efficient drive.
Yep, it handles all the logistics behind the scenes.
If they successfully daisy-chain them like that, they must have saved a ridiculous amount of hardware, because now you don't need dozens of GPUs just to hold the 5.4 terabytes of data.
The efficiency gains were paradigm shifting. For that massive 10 million token workload we talked about, the H-cube system processed 18.8 times more simultaneous queries than a system using only standard memory.
18.8 times.
Yeah. And just as you deduced, a workload that previously required a massive cluster of 32 GPUs was handled by just 2 GPUs.
Wait, really? Taking a 32 server rack down to 2 boxes? That is insane.
It is, which ultimately boosted the performance per watt, the total energy efficiency of the entire system by 2.69 times.
Okay, the H-cubed architecture solves the general memory capacity problem beautifully. But what about highly specific tasks where AI has to mathematically search through millions of private proprietary documents? Like, if you aren't just reading static rules but actively hunting for specific data points, does this daisy chaining still hold up?
That introduces a different kind of bottleneck entirely, which actually leads us to another major breakthrough. There's a paper published in the ArcSuv repository by Pokai Su and his colleagues. They introduced the Haven architecture.
The Haven architecture, right.
It tackles vector databases, which are heavily used in a process called Retrieval-Augmented Generation, or RAG.
RAG is incredibly common in enterprise AI right now. It's basically when you give an AI a specific set of private documents like your company's HR policies or, 10 years of legal contracts, and you ask it to answer questions based only on those documents.
Right. And to find the right information instantly, the AI doesn't just read the text like a human would. It turns every sentence into mathematical coordinates called vectors, plotting them on a massive multidimensional grid. When you ask a question, the AI converts your question into a vector and searches for the coordinates that sit closest to it.
Right, so it's doing intense geometry on millions of data points to find the closest match.
Exactly. But because HBM is too small to hold a billion-scale database of these coordinates, older systems had to send this massive amount of data over something called a PCIe bus. That's the physical data highway on the motherboard connecting the storage drives to the main processor.
And compared to the elevator shafts inside the chip, the PCIe bus is like a congested, single-lane dirt road.
That's a perfect analogy. Sending terabytes of geometry data over that slow highway to the main processor to do the math just crippled the system's speed. The transit time alone caused massive latency delays.
So if the PCIe highway is the problem, Pokai-Su's team must have figured out a way to completely bypass it. I mean, you can't widen the highway easily, so you have to stop the commute.
They stopped the commute by putting a near-storage search unit right inside the logic base of the HBF stack itself.
Wait, they put a mini calculator inside the storage drive?
They did. Instead of moving terabytes of data out of the memory over the slow dirt road to the processor, they just sent the tiny mathematical request to the memory. The memory drive did the exact Euclidean distance math itself, right there on the dock, and only sent back the final answer.
Which means the bulk of the data never moved at all. What did that do to the latency?
By eliminating all that off-chip data movement, Haven improved the throughput by 20 times.
Wow.
And because the data never traveled the PCI highway, it reduced the latency, the delay in getting your answer, by a staggering 40 times.
A 40x drop in delay just by processing the cargo right on the dock instead of shipping it inland. This is incredible engineering. But let's zoom out and look at the bigger picture here. Why should someone using a smart assistant on their phone or writing emails with AI care about through silicon vias and near-storage search units?
Because high-bandwidth flash is the key to democratizing advanced AI. I mean, by solving the memory wall and dropping the hardware requirements from 32 GPUs to 2, we are drastically lowering the barrier to entry. Running massive, highly capable AI models won't require billion-dollar, power-hungry server farms anymore.
It's basically like giving the AI the pill from the movie Limitless. Instead of the AI having the memory of Dory from Finding Nemo during long tasks, constantly forgetting what you said 5 minutes ago, it can now instantly recall entire libraries of documents, books, and your entire chat history with zero stutter. The tools we rely on every day are about to become infinitely more context-aware and reliable.
And the global technology industry recognizes how critical this is. This isn't just an academic exercise confined to a few research papers. The memory industry is urgently working to standardize HBF right now. They've launched a dedicated workstream under the Open Compute Project, or OCP.
Which is a huge signal, because they are completely bypassing JDES, right? The traditional standards body for memory. JDEC's consensus-driven process can take years to finalize a new hardware standard.
The AI market simply cannot wait years. By using OCP's goal-oriented workstreams, fierce competitors like SK Hynix, SanDisk, and Samsung are actually collaborating and iterating in real time. Their stated goal is to get commercial AI inference devices powered by HBF to market by 2027.
2027, that is essentially tomorrow in the hardware development cycle.
Yeah, it really is.
So let's bring all these threads together. If we look at the core of our deep dive today, 3 massive takeaways really emerge. First, the AI memory wall was forcing scientists to choose between the blinding speed of HBM and the massive cargo ship capacity of traditional SSDs, which was creating a massive bottleneck for AI development.
Right. And second, high-bandwidth flash elegantly combines the two. By vertically stacking 3D NAND flash and drilling microscopic through-silicon vias down the center, engineers achieved Ferrari speeds with massive capacity, entirely sidestepping wear and tear by using it as a read-only library for inference.
And third, hybrid designs, like the HQ'd architecture in Haven, are totally rewriting how supercomputers are physically built. Putting massive memory right next to the compute chip, or even putting the calculator inside the memory itself, is saving massive amounts of power and erasing latency.
It really forces us to rethink what a technological breakthrough actually looks like. Innovation isn't always about discovering a brand new material or inventing a completely novel paradigm from scratch. Sometimes true scientific genius is taking a reliable, everyday technology like standard flash memory and re-architecting it in 3 dimensions to solve a modern bottleneck.
It's taking the tools we already have and building upward instead of outward. And if this physical discovery is just the beginning, if AI can now access millions of pieces of context instantly with practically zero latency, what happens to human interaction and creativity when we're collaborating with a digital partner that literally never forgets a single detail?
It's a wild thing to consider.
It really is. Think about that the next time you boot up an AI assistant and wait for that cursor to blink. Thank you for joining us on this journey in the Deep Dive Lab. Make sure you follow and subscribe so you don't miss our next deep dive into the hidden science shaping our world. Catch you next time.